So, hello everyone. It's my great pleasure to introduce Professor Mani Shrivastava. Mani is on the faculty at UCLA, where he's associated with Department of Electrical and Computer Engineering, as well as the Department of Computer Science. I actually came to know Mani since 2012 when he hired me as a graduate student to pursue my master's and PhD in his group. So, thank you, Mani. His research focuses broadly in the area of human cyber physical and IoT systems that are secure, privacy-aware, machine learning-enabled, and application-driven. It spans problems across the entire spectrum of applications, architectures, algorithms, and technologies in the context of systems and applications for M-Health and sustainable buildings. He is the fellow of both the ACM and the IEEE. He has a very long list of awards, including 15 Best Paper Awards, and today he's going to talk to us about his work on quality of time and its applications. Please join me in welcoming Professor Mani Shrivastava. Thank you.
Thanks. It's always a great pleasure to come to UC Irvine. I envy the open spaces out here relative to UCLA, so nice to be here. And thanks for the kind intro. Actually, Yasser was also my student, so I have lots of connections down here and many friends and collaborators. So this work that I'm going to describe is actually one which is a large project involving several universities, which we've been doing for the past 5-ish or so years, and so in a way it's kind of like a cap of what we have accomplished. And needless to say, therefore what I'm describing is obviously not my work, my students, but students of also collaborators of mine at CMU and San Diego and Utah and Santa Barbara. So these were the 4 other institutions. So what this is about time. In particular, kind of we started with the observation that time plays an incredibly important role in a whole variety of different systems that sort of I have listed out there. In particular, sort of firstly to the first order time sort of within a single system matters to meet deadlines, things like that. But particularly systems that are either interacting with the physical world, because then time enters indirectly when you are sensing something, when you're controlling something, sort of t is always a variable or delta t is always a variable of interest. And then the other place where it becomes important are systems that are distributed, because if different computers engaged in that collaboration have different notions of time, again kind of bad things happen even from a logical perspective. So time clearly is important, and what happens, sort of we dig deeper down, as I showed here, there are kind of a few main reasons, right? This choreography of actions, figuring out the events, and kind of making sense of the physical world. And under the hood, there are really kind of 2 main things which come together to give computer systems a good notion of physical time. One is the basic clock technology, kind of the oscillators and sort of the circuitry surrounding it, which lets us figure out the passage of time. And then you need some protocols and all which sort of talk across both different computers, and also between the hardware and kind of your applications which are running within the computer to kind of give sort of a uniform sense of time and associated variables like frequency and phase, so that depending upon the application needs, you can do things meaningfully. So and in particular, if you kind of if you have done any course in distributed computing, there's a lot of time spent on things like consensus and sort of making sure that your operations have the right properties, they are ordered right, and they have the right atomicity and all. A lot of those problems become considerably simplified if imagine an ideal world where everyone had a precise notion of time, right? Everything was, the physical notion of time was precise. So then if you are trying to figure out the ordering, all you have to do is consult your local time service, you'll get a timestamp, and you will reliably know that that timestamp relative to the timestamp at another computer would have the right properties. So in a way, you could argue that maybe we have just shoved the problem one level deeper. Some sort of timing service gives us these magical properties. So increasingly, we do see in distributed systems this trend towards making use of precise timing services that are available. In particular, GPS is around us, and it does give us kind of a planetary scale timing service, while we call it positioning system, but deep down it's positioning both in space and time, and GPS fundamentally does give you the ability to have a timestamp, which is kind of around, let's say, order of 50 nanosecond, a small number of tens of nanosecond accurate. So lots of wonderful things can happen, so instead of lots of communication, now we kind of shift the burden to things which are happening locally. So, and in particular, kind of interest to what the kind of systems that my group has been engaged in are these cyber-physical systems. So now they kind of bring together both these properties. They're distributed and they are interacting with the physical world. So imagine like smart city kind of context, problems like controlling transportation or kind of fleets of drones and all these kind of problems. They kind of bring together both these attributes where kind of time plays an important role. And if you kind of look across the space of applications, you can pretty much at any sort of corner of how much accuracy you need in terms of time and what's the spatial scope, there are interesting applications which abound. And moreover, a lot of times we're trying to do these applications not with sort of custom-built hardware and software, but really with on a general-purpose platform. Often even incorporating cloud services, virtual machines running out on Amazon or Google substrates and things like that. So these systems are prevalent. Time plays a very important role, and increasingly we are using them in settings where kind of the opportunity to just create a point system is not that great. So lots of examples. I've already talked about it. Now sometimes time goes bad, and variety of reasons. Sometimes the clocks go bad, and sometimes kind of the network goes bad, and therefore things don't work out. Many instances in just recent decades where bad things happen, and you kind of go dig a little bit deeper, and the cause was the system had a bad notion of time. So you see kind of top left, kind of an infamous incident from, I think it was the first Iraq war, where kind of an incoming missile hit the base in Saudi Arabia where US troops were forced, and it was basically about tracking anti-missile system, tracking the incoming missile. And it so happened that the way the software was written, there was a tiny buildup of error in each compute loop, very tiny, but the longer the system was running, the error builds up, and it so happened that that particular day when kind of the missile was coming in, the system had been running for a long time. Usually it would crash before and they would have reset it. So there was substantive error, and so that resulted in sort of imprecise tracking of the incoming missile, and therefore they failed to intercept. Sometimes time, the value of time that the software has is bad because of human errors. So a couple of years ago, there was an episode where they were updating the software on the GPS satellites. Again, for whatever reason, that process didn't go as intended, and there was a tiny error, 13 microsecond error in GPS time over some part of Earth, which included UK and some parts of Europe. And again, GPS time is used by many communication systems and all, and it kind of brought down BBC radio and things like that as a consequence. A more interesting example, again from roughly a year and a half ago or so, in a hospital they were repairing an MRI machine, and what happened was I think some liquid helium or liquid nitrogen kind of leaked into the track system, and all Apple devices stopped working, or whatever typical iOS devices stopped working. And it turns out that Apple tends to be more aggressive technologically, so they have been using a new type of clocks instead of our standard quartz oscillators which you see in your electronics. There is a new generation of clocks which are based on MEMS technologies, where basically there is an oscillating thing right on the chip. Unfortunately, when molecules get in, it kind of gunks the mechanical stuff, and therefore they stop working. Apple has been using it because these things being on chips save volume and size and power and stuff like that. Okay, so enough motivation. So clearly, sort of time plays an important role in our modern system, and lots of technologies. I mentioned DPS, but there's a whole bunch of other technologies which in recent, let's say, decade and a half have emerged. CSAC, for example, stands for Chip Scale Atomic Clocks. There was a big DARPA program which kind of funded because the radios that soldiers carry when they network, you can save a lot of power if the radios have a good sense of time. Imagine when they're transmitting packets, if I don't quite know when the sender is going to send a packet out, I'm going to wake up a little bit earlier and therefore end up wasting energy. So CSACs were developed in part to meet energy efficient communication needs. Synchronous Ethernet, again sort of creating time aware network system. And perhaps the most prominent one has been this IEEE 1588 or precision timing protocol. This allows kind of sub-microsecond type things in a local area setting, and with careful tuning and all, like organizations like CERN, the particle accelerator collider in Europe, they achieve picoseconds over kind of a few miles kind of range because they're trying to do atomic particles and those sort of things. So there are all these technologies that have been there and taking care of these different applications I talked about. But meanwhile, what's also happening is that we are trying to design these kind of time-aware systems using technologies which are kind of messing up this process. So we have precise technologies for getting time, clocks and protocols and things like that, and then we have these applications. But in the middle, we are facing things like we are trying to run things on virtual machines, where one of the things for virtual machines to do not do easily is to get a good sense of time. We shut down our processors, we change frequencies of processors, all in an attempt to make our systems better. So, kind of lower end is improving, applications are becoming more critical, but this kind of middle stuff is introducing increasing amount of uncertainties and all. So, in particular, the manifestation of that is that when we write time applications where time plays an important role, at a software level, we often just think of it as, I can ask the system for the time. What time is it? All your programming languages and OS, they provide some sort of API, like get time of day or sleep for 5 seconds, and these kind of API functions exist where time has a role. And our systems give the illusion as if it's very confident about this thing, right? You write get time of day, you get this sort of multi-digit number or data structure, and as if it's totally accurate. The reality though is that there's a lot of variations. Frequencies change, the degree to which you are synchronized with other systems change and all. And so the net result of all of that is that you can't really trust this number. There's a lot of uncertainty that exists around it. And that's what we are going to talk about in the rest of this conversation. So if you dive under the hood, traditionally when we think of sort of computing systems, we just think in terms of processors and an OS which is trying to schedule things and all. But a big part of modern operating systems, even kind of the ones like Linux and all, is devoted to this issue of how time is managed. So deep down at the lowest level, there is obviously some local source of oscillation, right, which generates a periodic waveform of some form, goes through some sort of driver circuitry. At the end of it, you get kind of a clock wave, which is what, if you've done a digital logic course, think of as a clock waveform. It then drives some sort of a counter, that counter then results in some sort of interrupts, and all this process goes all the way up to the software, and that's where sort of at the software level we get to see those APIs and all we can talk about. And indeed, over the years, historically, lots of optimizations and all have done. In recent years, let's say recent 10 years or so, the Linux operating system, there has been a lot of refinement under the hood, because as these new things like precision timing protocols and all have emerged, the clocking system within the operating systems have become far more complex, and that simplified view that I gave. So for example, your Ethernet cards nowadays have very precise time stamping capabilities. When a network packet comes in, it gets time stamped, and it plays a very or can get time stamped, and it plays a very important role in doing precise synchronization. There are applications in, for example, financial industry and all, where going down to some microsecond or even tens of nanoseconds is often legally mandated. And then you need to synchronize what the network card knows and what the CPU knows. So all of this thing is supported by a pretty elaborate timing subsystem that kind of exists. But unfortunately, all of confounding all of this picture is kind of two main sources of uncertainty that kick in. One is the clock, that oscillator that we have down there at the lowest level. These things are not perfect. They notionally have some frequency, but the problem is that because of manufacturing and physics-related variations, even sort of two copies of the two instances of the same type of oscillator will have differences, and the same oscillator over time will change with aging and with environmental factors and things like that. And the other confounder which comes in is our ability to synchronize two clocks. There really is no such thing as perfect synchronization, and in fact, even in physics, there is this whole concept of Einsteinian synchronization, which kind of comes from more relativistic perspective. But trying to synchronize two clocks is basically there's some irreducible uncertainties that just sort of very loosely speaking. If I have two clocks, and let's ignore all those relativistic effects and all, if I have any asymmetry in the round trip, that is, if going from A to B and B to A, there is some asymmetry, then that's an irreducible, some asymmetry and we don't know what it is, then that's an irreducible error that will always exist. You can't just get away from it. So these two things compound together. So my frequency is unstable and sort of not across different computers. There is some variation, and the other one is that this inability to really, those equations are written, they basically are at the heart of any synchronization protocol. They basically say we can exchange in a bidirectional message exchange, timestamp every arrival and departure, and we can solve those equations to get the offset between two equations. The problem is that if there is an asymmetry in the delay, then you end up with three variables in two equations, and you can never solve it. In more, in a networking sense, another way to saying is the following: that if I want to find the one-way latency between two computers, what's the latency from A to B, you can't do it without some other additional assumption. So either having synchronized clocks or some other assumption. So uncertainty exists, and as a consequence, when you look at how the relative time between two computers, there's always be some sort of a distribution around it. You just can't compare timestamps directly. So all these different factors that I have listed sort of come into play. I mentioned about the asymmetric delays and variable delays and imperfect oscillators and all these other factors, as well as some more recently kind of things like attacks happening on the system. So if applications depend critically on time, then as you might imagine, someone who can subvert the notion of time can therefore indirectly subvert the application also. So normally we think of sort of security, kind of messing with the data values and tampering with them and all, but time, which is being used by the applications, is another such vector. So what's the implication of all of this uncertainty? So just to take an example, let's imagine it's a simple, some sort of a control system. So there's some kind of physical plant, you're sensing it using some sensors. Sensors send the data to some algorithms. Nowadays, kind of those algorithm sensors are very sophisticated, and then kind of they decide how to control the actuator, and then the actuator in turn acts back on the physical plant. So first kind of issue that you might imagine out there is that because of networking related issues and all, your synchronization may not be perfect, and therefore the timestamps, which a sensor may timestamp a reading by inserting its local time service, but then when the algorithms and the controller are operating on it, if those timestamps have an error, then the algorithm kind of goes, will not do its job correctly. and so on and so forth. So this uncertainty begins to affect how your application will behave. In particular, as you might imagine, if I have a sensor that says that the reading was at time t, but actually there was an error of delta in that time stamp, then you can equivalently think of it as if there was an error in the value that was being given. So you can think of the error in time really being given some model of the signal as being error in the value, and therefore it will that's a deep down source of the problem solving. So we had been building these kind of systems and all, and sort of my group and sort of the people we ended up collaborating with, and we were also working quite a bit on kind of things like time synchronization and all, but kind of an idea emerged, and which is what we chased, and which is how do we handle this uncertainty? So instead of simply kind of saying, hey, let's try to keep chipping away at this uncertainty and reducing it, but we were first facing all these brick walls of sorts. So we decided to kind of take a different approach. Let's make this uncertainty explicit, observable to the applications. So and then moreover, let the applications also specify what they are able to tolerate. So currently, for example, application may say sleep for 5 seconds or wake me after 5 seconds or stuff like that, right? What do they really, what's the tolerance, right? I mean, when an application gives me some deadline or some timeout, is there some laxity which is allowed in it? So make uncertainty explicit, make it tunable. So if the OS and the hardware knew what is needed, then we can accordingly tune how we are operating the lower layers. Perhaps we can activate a lower power, less accurate clock. Perhaps we can synchronize less often and then wait and avoid the network wastage that might otherwise happen. And kind of have this uncertainty be shared across a distributed application so that we can coordinate what is happening on a network scale. So that's what sort of we started out with. And the idea was that we take a whole bunch of different applications and then really kind of explore how this concept of making uncertainty explicit, tunable, sort of is going to work out, and look at different kind of issues out there. So variations that are happening, things which affect the integrity of time, and sort of just all sort of other issues which sort of come up in this process, and try to distill it out.
Quick question.
Sure.
Are you not looking for probabilistic cavities? Would that be the direction you're looking also, or are these probabilistic cavities?
This is so probabilistic notions of uncertainties. Yeah, that's okay. That gets subsumed under it, depends upon how you capture, how you specify that uncertainty. Although we took a deterministic approach, so people will. But the problem is probabilistic still only just gives you a probabilistic experiences, and so in many cases where you do need some sort of harder deadlines, it doesn't quite work out. So we kind of got inspired by a very famous piece of work from Google called Spanner, which is basically about synchronizing data across data centers, so distributed databases. And the problem you face there is that you have all these transactions happening at sort of different sites, and you want to reconcile them so that the end effect on the data is as you intended, right? So that this read happened before write and things like that. And traditionally, this has been done using various atomic protocols and things like that, so all handled at a logical level. But what this spanner work and the underlying thing called true time did was the following. That you know, GPS is pervasive, so we can assume that the different data centers have GPS, and so they have a notion of time. Except that this time has some uncertainty, particularly because, like I said, GPS gives you like, let's say 50 nanoseconds or so, but it kind of varies under different factors and things like that. But what Google did was they basically said that, look, if we engineer around this uncertainty, there are a lot of cases where we were basically falling back on protocols to resolve the ordering and all. We could get rid of that, and only if the transaction timestamps were close enough for us to believe that we have ambiguity, would be resolved to some protocol to resolve it. So TrueTime API that we had essentially exposed the uncertainty in the GPS time to the database, and thereby the sort of that distributed database kind of made use of that. So that was an example where exposing uncertainty clearly was having benefits, and we kind of built upon that. So we generalized that notion to something that we began to call as quality of time. Kind of a play on obviously quality of service that people in networking use, which usually refers to things like what sort of latency, throughput, those kind of things. Here it was explicitly about with what quality a system is maintaining time and what quality an application needs time with. So imagine for practical purposes that wherever you have a time variable in any interaction between an app and the underlying hardware and operating system, we are going to replace it by something which also indicates uncertainty. And you've got many different ways, but let's imagine for now maybe it's just an interval, right? It's just sort of simply saying, wake me up in 5 seconds. I can say wake me up anywhere between 4.9 and 5.1. But you can imagine other ways of doing it in terms of accuracy, resolution, things like that. And then we sort of introduced this notion that we call as timeline, and I'm going to talk about it. But the idea is that an application, a distributed application, or even a local one, can specify kind of its own virtual time coordinate with the associated quality properties, and then give it to the operating system, and let the OS kind of have the job of maintaining this. So as opposed to currently, where sort of typical OSs expose a clock, or in some cases in Linux there are 2 or 3 different types of clocks with different properties. So like in Linux there is a clock which is monotonic, and there's a clock which can be non-monotonic, okay, but has. So in one case you have sort of clock always advancing, in another case it may be more precise versus more jumpy because as the system runs more. So there are clocks of different resolutions and things like that, but they're kind of fixed. What we introduced is this notion that we can specify our own virtual timeline with the associated quality properties, and then sort of leave it to the underlying system to take care of it. So that's what this project that we have been engaged in with sort of a whole bunch of collaborating universities has been chasing. It's a project called Roseline. Roseline refers to this prime meridian, which in Europe, and so there's a play on it, but kind of the vision was, let's talk about this uncertainty. So let me start with so what this timeline does. So timeline essentially is a OS abstraction that we introduced, implemented in Linux in various ways, and it basically allows to create a timeline essentially and bind to it. So one part of our distributed app can create this timeline, other parts of other computers can sort of bind with it, and then you specify to what degree to what quality do we want the time in this case. Our implementation actually is in terms of resolution and accuracy, and then under the hood there might be multiple timelines depending upon their applications, the different requirements, and the operating system maintains them. So the kind of things we end up controlling in this case is what clocks we are using, there are many systems that can be created now also have multiple sources of clocks, what synchronization protocol we are engaged in, and for a given synchronization protocol, how frequently we are synchronizing. All of those things become sort of controllable. One of the things that we make... Yeah, sure.
So, in this concept of pushing the timeline into the operating system and having it deal with some amount of uncertainty, is there an underlying assumption that there is some other background global protocol that's trying to make something like GPS
No.
that provides that kind of baseline upon which the uncertainty is?
No, so it's always relative to some reference node. So when we define uncertainty and all among a group of nodes, we're basically talking about the spread within that group. Okay.
So there is no external.
It's not excluded. So you can have one node be a reference because it has a GPS or atomic clock or whatnot. But the basic primitive basically is purely in terms of the nodes which are engaged in that timeline, and the accuracy is really in terms of the spread among those nodes. But if one of them happens to be your GPS node, then basically you are saying relative to global time.
Because the early Berkeley Unixes had this kind of aspect where they would have, one of the nodes might serve as a master and coordinate it.
So NTP operates like that fundamentally, right? I mean, there is a set of servers which are tier 1 or stack of 1 NTP servers, and everything either directly or indirectly kind of refers back to that. But if you think about it in a lot of applications, right? So fleet of drones, all that matters to coordinate them is this, and not really what the global time is. So we started with this notion that let's not make the global notion of time mandatory, but you can introduce it if necessary.
So you mentioned that the uncertainty was captured as an interval.
So it's explored both the interval or resolution plus accuracy. These are two abstraction explored.
That itself can vary over time. Right?
For an application, so an application needs may change, as well as the system's ability to sustain it can change, right? I mean,
Right,
so
underlying hardware. So are you introducing some notion of updating?
yeah. So what happens is if the underlying hardware or the system is unable to meet it, then an event goes back on the processes associated with that timeline. That now we are making the quality is worse and we can't meet it. So we have both, right? The application can update the spec, and the reverse direction if the system cannot meet it. Then so much like QoS systems are designed, right? And there's bi-directional engagement that happens. So it's literally we kind of took that paradigm out here. And under the hood, what we do is all the clocks in the system, very loosely speaking, in any given computer system, is either just a processor clock, or in many of our systems now there's a processor clock as well as a clock on the NIC, the network interface card. And we kind of, the way the synchronization happens is, on a computer, a processor clock is synchronized with the NIC clock, and then two NIC clocks from two different computers get synchronized, and so that's kind of the pipeline that happens. But in many cases, the NICs are dumb, they don't have any local clock, in which case you are directly synchronizing just with the processor clock, but then less accuracy. So many embedded systems now, actually, if you look at the Ethernet specs, they actually support Ethernet level timestamping. It does require digging a little bit deeper into it, but you can get into nanosecond level synchronization over local area networks in that case. So we make heavy use of that. And then you might imagine, this is just a notional picture, but where kind of a large scale distributed system may have these different islands with different timelines. And sort of using our approach, those timelines get instantiated. Each timeline may have different member nodes, and kind of we just optimize among that set. And this is just a glimpse at the API, but basically don't bother reading it. But basically, we create a timeline, different elements bind to it, and then there are API calls to adapt the spec, to get notifications back, all those kind of things that one might expect. So now on to realizing this thing. So essentially you can think of that timeline is a way for us to provide time as a service with certain sort of service quality specs associated with it. And we kind of created 3 different variants of it over time. The first one of which is one by my group, and the other 2 are from QuartzV, and we collaborate. So we started with sort of within Linux, and in particular, if any of you have used these BeagleBone Blacks, a very popular embedded system platform. So that's what we use in this case. It's a stack for Linux. Then we move to stack for VMs, both where you have para-virtualization as well as where you have to do full virtualization and with different things, different quality levels that we achieve. So mention that, and then finally, Sandeep, this is our CMU, sort of, we also created this kind of planetary scale kind of thing where we can really kind of take widely distributed services and provide this. So let's talk a little bit about it. So our basic building block is the QOT stack within Linux, and in essence, what happens is a kernel module we have created, which we kind of call the QOT core, which interacts with the timing subsystem in Linux to provide all these things that I kind of mentioned, the ability to create timeline, control it, interact with it in different shapes and forms. We support both ARM and x86 platforms, and basically, since it's a kernel module, we really don't make any changes to the mainline kernel code. And with this, we are able to provide things where for different timelines there are different specs, and kind of those plots like on the right are intended to show that we are able to achieve those. So in the sense that the goal is that whatever uncertainty band application allows, are we able to achieve an operating point which is within that. So that's been kind of the goal, and you kind of see this example, for example, where the lower bound and upper bound specify, and using our system observed, and in terms of uncertainty related to accuracy, and sort of again degree to which you can control things, and then finally all of this. I mean, you can argue that okay, an application could do entirely at the application level, but essentially we are factoring all of this into the service, and so it kind of simplifies writing of applications quite a bit. So once we had this kind of main Linux level stuff in place, then we went after doing things in virtual machines, and kind of the motivation was that nowadays a lot of sensing and control applications involve some piece running on either edge server or even out into a server out in backend services, and sort of you have all these issues like multiple VMs sharing a resource, and also one of the things, if you read the VM literature, virtualizing time is kind of incredibly hard, just because exchanging time information between the hypervisor and kind of the VM results in a lot more uncertainty if you don't do it carefully. What exactly should happen there has been a subject of a lot of debate. So in our particular case, working with QEMU and making use of para-virtualization, we provide sort of lots of traits of shared memory and all. What students implemented is something which is almost near native ability to the virtual machine to be able to read the time at the host level. So in effect, then the timeline within the virtual machine is now being we can sync it with what is happening in the physical machine level, and yet maintain all that isolation and portabilities that you expect of the virtual machine. So that's what I wrote. Now, unfortunately, in some cases you don't have para-virtualization, so you need to do full virtualization. In which case, in essence, we kind of run a synchronization protocol between the VM and the main machine, and then accordingly kind of a lower level of performance, but still maintaining full functionality. So so what you see out here is kind of the performance levels that you are able to achieve. So what on the right that you see is kind of the para-virtualization case, where you see kind of our performance is basically at the same level as our normal sort of Linux stack, but with full virtualization kind of we take a hit just because transfer of time information between the VM and the host itself is introducing uncertainty. Some more examples where now we subject it to network stress, so there is interfering traffic, stuff like that, and then how are we performing with those. Main thing to look at is the black line is what the system actually achieves, and sort of how we are between, are we able to operate in the desired band. Okay, so the final one in that thread is timelines operating over kind of geo-distributed scale, much more spread out kind of things. And in this case, we kind of create a hierarchical sort of solution at different layers. And kind of the idea is that in essence, you can imagine once we have sort of this timeline as service, then on top of it, you can build all sorts of other things like coordination services and all that are physical time aware. So that's what this Quartz finally does. So you can have all sorts of different things, different sort of physical machines, within a physical machine, multiple VMs and containers and such. And our basic thing is this adaptive, this timeline which kind of adapts to whatever the basic realities are. So one thing it does in these geo-distributed timelines is at different places it selects intelligently what time synchronization protocol makes sense. Some places NTP, some places PTP, and some places just even customized protocols. And the other thing which does is kind of depending upon the type of virtualization and all, it basically adapts the time transfer at that boundary. So what you see out here is that we are able to kind of adapt our performance, and in particular kind of operate at many different scales. So at continental scale, so like let's say this country, we able to provide generally able to achieve things at milliseconds level, or sorry, some millisecond level. And if you go planetary scale, kind of obviously things degrade, but still from an application perspective, it's a nice coherent viewpoint. Using this, we have explored a variety of different applications at different scales. So one is basically coordinated robotics, where you have multiple robots, each having their own virtual machine controlling it, and then we are trying to coordinate among them, and in which case sort of this geo-distributed timeline comes into play. And a variety of other ones that we have explored. Okay, so what timeline provided us is kind of this software abstraction with we can sort of let the application and the system interact in different ways. So the other aspect that we have been pursuing in parallel is how do we improve quality of time, or how do we cope with quality of time, right? I mean, the timeline itself is more of a resource management play, right? I mean, it's basically saying let's make it visible, let the application, so the application can adapt to it, and the system can adapt to the application needs. But orthogonal to that is this whole issue of whatever QoT is being seen, how do we interact with this? So I'll give you a few examples from across our team. So one aspect that we explored, and we kind of chanced upon it, is distributed sensing applications involving phones, or phone-like devices. Okay, so sort of, as you know, sort of lots of apps on a single smartphone, picking up data from the sensors and all. But also there are a lot of apps where data from different phones, different users' phones, get synchronized to about some physical space. And when we started down this path, very rapidly we noticed that oftentimes we were seeing what we thought were kind of near simultaneous events. Actually, there was significant sort of time gap in it. So, and unpredictably so. And I'll talk about why that happens in a moment. But now imagine you have a machine learning model which is trained, assuming sort of your time series from different sources were actually nicely synchronized, but then at test time, the timestamps are kind of messed up. So now you're feeding it to a model where your time series are shifted, and of course, if they're shifted sufficiently, then your inferences are going to take a hit. And likewise, we often collect ground truth data. So what happens is our subjects in our study have smartphones with sensors and all, and then some other device you kind of do the labeling. But again, if this kind of error occurs, then your labels are actually misaligned with what is under the hood, because they are just on different devices. So, and so as you kind of increase the uncertainty, the synchronization error, kind of the performance at test time kind of begins to go down. So first thing we did was we kind of tried to figure out what was going on. And it turns out that Android OS itself plus some pernicious interplay with the way time synchronization protocols work, can often lead to errors as much as 5 seconds between two devices. So what happens is that there are two main protocols for synchronization: NTP, which is over the internet, and there's something called NITZ, which is what for the cellular systems. And of course, your phone may have a SIM or not, may be on Wi-Fi or not, so there are all these different permutations which are possible. And for some unknown reason, the way Android operates is that under circumstances, it may essentially let the error related to NTP build up to 5 seconds before it corrects. So instead of doing continual correction, it kind of lets the error build up. So you see out here, these are from experiments where we basically use an external stimulus to kind of make sure they are all on the common time base. You see a couple of these devices which are suddenly kind of resetting. Okay, so and the fix is fix that part of Android OS, but I guess what it's showing is that our devices are often not designed for the kind of type synchronization which are important for CPS type applications. And even otherwise, there's a fair bit of spread. As a side note, actually Apple's devices do excellent in this regard, as long as they are not, I guess, other than some iPads which are only on Wi-Fi. Okay, so I think they're just more carefully engineered around these kind of issues. So how can we go around dealing with this thing? So first approach is that, stop trusting the system time, because as we see in the case of Android at least, it's pretty tricky. So in effect, at the application level, you directly take over the burden of checking the time. So we kind of did that. We basically created a user space NTP library so that the applications can take care of it. And with NTP, you can get into, let's say, order of 50 to 100 millisecond type accuracies reasonably well. For some class of applications, that's actually pretty decent. For nearby phones, you can also make use of the peripherals. So your only way of synchronizing is not simply NTP and via a data connection. You can also imagine common sensor events. So like if two phones hear the same sound, that's an opportunistic synchronization event. Or if both hear the same Bluetooth beacon or something like that, again, that's a synchronization event. So for more precise, more precise synchronization between nearby phones, you also have this additional pathway of making use of these peripherals to achieve things. And with this, we can get to sort of significantly better, order of magnitudes better than what you would otherwise. So you kind of see some examples out here. The third approach which we have been exploring is much like when you are training a model, we kind of subject the data to various kind of perturbations. So like you subject the images and all to rotations and translations and all, just to create a more robust model. What if when we are training, we were to subject the time series data to shifts and all, so that we create a more robust model? So this slide kind of shows that, and of course there are a lot of under the hood nuances, like what kind of activity we are worried about. So if the activity I'm trying to classify, let's say using some inertia sensor data, is a long-lasting activity, then obviously some small shifts are not really going to matter. But if on the other hand we are using accelerometer for things like gestures and all, short-lasting activities, then even tiny shifts begin to have a huge role to play. So it's all relative to your application. Some current work we are doing, we're kind of looking at this issue of when we transfer reinforcement learning policies learned under one setting and then we move it to a different setting, what impact this shift ends up having. Okay, the other thing which my colleague Sudhakar Pamati has been doing is just improving the clocks themselves, right? I mean, what I described thus far is more kind of the system level issues, but we could also go around improving the clocks. And in this particular case, we have kind of developed a variety of different clocking architectures designed particularly for IoT devices. So in particular, one of the challenges, so we started out with this notion that maybe we can have a bank of clocks with different quality power kind of trade-offs. And then pretty soon we realized that the startup time of the clocks was pretty problematic. So we couldn't just like you can stop a processor by stop supplying a clock, but stopping a clock is more problematic because when you power it back on, it takes time for the oscillator to become stable. So one direction that we went after is clocks which we can start very rapidly. So we can power them off. So this enables having kind of a clocking subsystem where you can have these choices of clock. And the other direction that we did was, while the system is notionally asleep, we want to maintain time with very high accuracy. So if we, a lot of these edge devices, IoT devices, we put them to sleep, but if you kind of dig deeper, oftentimes your bottleneck becomes the clock itself, because you still need to maintain a notion of time, because otherwise you can't even do things like wake up after an hour, right? So you need very low power clocks which can maintain time sufficiently well for you to be able to do things which need to be done while asleep. So that was the second thing, sub-nanowatt type real-time clocks, which we can basically just keep powered up while the rest of the system is asleep. So pretty cool work. We made chips and systems around it, sort of a couple of papers at last year's ICCC around it. Our third piece of work has revolved around time as an attack vector. And there are many different ways time can be attacked, and in fact NTP was designed in a very innocent era, so where people never bothered about these issues. So actually there's one line of work that some people have been exploring is kind of basically identifying vulnerability in NTP, which is kind of the fabric of time for the internet, and lots of issues there. Now, some of them are just really obvious design issues, but there is one attack vector on time which unfortunately is very pernicious. So go back to this whole synchronization story, right? The way we synchronize is by exchanging messages. So of course one attack would have been I break the crypto and mess with the contents of the messages. But we know how to do crypto pretty well, in particular, right? So that attack vector is fixable. What is not fixable is some adversary adding this, capturing the packet and transmitting it up, introducing a delay. Okay, so just man in the middle attack where we don't need to break into the packet, just delay it. And if you just delay it, then you have introduced kind of a different notion of delay, and therefore the clock offset that will be computed is going to be incorrect. So, there are many different ways of attacking time. And the implications of them, right? You can violate rights management, you can forge timestamps, you can falsify location, anything which any system service, security protocols make use of timestamps. All of them basically kind of become vulnerable, and with the variety of consequences. I'm going to skip through this slide. So what we focused on was the following. In recent years, there has been a lot of effort towards introducing the so-called trusted computing base or trusted execution environments, which are basically parts of our modern processor hardware where we provide an extra level of security guarantee so that even if the operating system is compromised, we still vouch for the application's integrity. So, for example, you have Intel SDX, Trust Zone, these sort of things, and kind of loosely speaking, like let's take Intel SDX as an example, even the OS cannot peek into the data that exists, that belongs to something inside that on-edge. But as we saw, for CPS applications, correctness is also a function of the time. So it's not sufficient to say, okay, OS cannot mess with the data. We also have to make sure that the application has a trusted notion of time. And so we started out with this notion that can we provide applications inside these enclaves with a trusted notion of time? Can we secure time? And if you kind of think back, then there are kind of a few essential elements for securing time. We need to have a trusted timer. We need to have a secure access to the trusted timer. I should be able to read the trusted timer without any interference. I should have the software itself for timekeeping, which is secure, and then finally I need to have access to some time reference on the network, which is secure. The problem out here is, okay, so SGX provides number one, trusted timer. It's very coarse, but Intel provides it as part of the microcode. Secure access to the trusted timer is a problem because in SGX, when the systems, you go through the OS, but we don't trust the OS. Number three, secure timekeeping software. In principle, you could because you can run it inside the enclave. Number four is again hard. Any network packet goes through the OS and therefore it can add these delays and all and mess with the version of time. So short answer is very there are all these different packet vectors which still exist. So if you're running a application which is sort of time critical inside these enclaves like SCX, you still are vulnerable because the OS or some other man in the middle kind of entity can still mess with the notion of time. So my student Fatima, who graduated last year, she kind of worked on it on this problem, and the system that she has created, TimeSeal, which basically what we do is we kind of make use of we essentially create our own trusted time base inside the SGX by doing clock counting and things like that. Okay, so we basically measure reliably the passage of time and try to overcome some of these properties. I don't have a time to go in details, but if any of you are interested, I can point you to papers. But basically, this is a sort of a first year attempt towards it. The main thing that I want to bring out is that there's a class of applications where you do have to protect the integrity of time, and a lot of issues around it are still sort of unresolved, and maybe kind of the answer in an ideal sense would be to actually these things be at hardware level proper services as opposed to what TimeSeal is doing, which is kind of wrapping around it to attempt to patch these problems. So in summary then, what we have been doing in this project really is to introduce this concept that, you know, time is uncertain, and instead of kind of papering over it, let's make it explicit, let's make it part of a contract where uncertainty is explicit in that contract, and then kind of look also at these ancillary elements like improving the clocking system, improving the synchronization protocols, and then kind of making the whole thing more secure. This has been a large project, so been great fun to interact with lots of people from different places, as you can see from this busy page. So what I kind of described is really a synthesis of sort of lots of activities which have gone on, and needless to say, NSF was very generous to let us explore this. So I'm going to stop with that, and any questions?
So I tried to get some intuition on if you're capturing quality of time as a metric, and you're doing this, if you go to slide 29, for example, where you're trying to look at capturing this at the level of multiple processors, I guess, just as an explicit example.
This?
Yeah, this one, yeah.
Okay.
So, it seems to me when you, I'm not sure if this is the right one, but you have to sweep under the rug with some, maybe, some margin, the idea that QOT itself does not face issues of oscillations and so forth, right?
Yeah.
So if you do that margining, then you're back to the same problem that you had before, because you have to build in these margins at every level so that you can consistently manage that without leaving it. So can you speak at a definition how you're managing that?
Yeah.
How are you getting away from that problem?
Okay, so I guess the thing is, can we give provable guarantees that under the operating conditions we are able to short answers? No. Okay, so these are empirical things. The reason is still, so do we violate? I guess my students claim we never violate, but of course that's not true. Okay, but I'll point to a different aspect, which is gap between the kind of purity requirements we see across applications is far more than what we are dealing with out here. So a broader concept that we need to operate at very distinct points, which range on one hand, kind of essentially subsetting kind of requirement, all the way to things where we are now fixing in order of tens nanoseconds, anything which is terrestrial localization kind of things and all. So that's a 4 or 5 order of magnitude range, and so gives us a sufficient amount of room to play. So even though, yes, to answer your question, we are brushing under the rug this issue that can I design a control time mechanism for kind of controlling things in timeline which will not violate. So our fallback right now is when we realize we are violating, we basically just inform the application. But I guess, the weak part there. But what particularly George is found out from Santa Barbara, that's kind of the complementary angle within this project, which is once the application gets the notification that, okay, this is uncertainty, then it adapts the algorithms accordingly. So what you've been doing is control algorithms where given the uncertainty in the timestamp, what should the controller be? So I guess that's kind of the follow-up approach. They leave it to the application to cope with that.
So I have a question about the ground truth. So when you say, okay, my quality of time is this, right? How do you measure and make sure relative to the ground truth, because you need to synchronize.
A very tricky question. Okay, so fundamentally there are two things that one can do as a ground truth. One is feed a common event to all the nodes and have some pathway through which I can maintain a system framework within these and then use that as a ground truth. And the other one is have all these systems give a heartbeat which we can collect with some instrument and assume for a moment these things are close by so that I can tie to a common instrument. That's what we do, but that's not sufficient because as we have also discovered that the I/O subsystems of our computers themselves have considerable uncertainty, particularly for things like smartphones where we really don't have that visibility. But that's for at least for smartphone class devices, we just have to live with it. For more embedded devices, we do have lower level controls, so like those bagel boards I talked about, there actually is some internal hardware where at the pin level we can essentially do clock cycle accuracy and something. So some class of devices we are confident, but our numbers on smartphones, like when we feed in this common acoustic event and it's flowing through, we are just able to kind of do some sort of average, create an average and use that as a baseline, but really we don't have any insight on something kind of, it's hard to define what is the ground truth in that case. So we are measuring the ground truth through a noisy channel, and I don't have a good answer there.
Any other questions? So, in general, large-scale distributed IoT systems, there's a lot of heterogeneity. So not every device is going to subscribe to a new abstraction or model of time. And so the question will be, in such an environment where, in some cases you have notions of uncertainty, but in some other cases you don't, how do you manage applications in this setting?
I haven't even thought about it. I guess, firstly, they can coexist. So that's not a problem. The only thing is that there are parts of my application that are running on systems which do not have this abstraction. Unfortunately, that whole application has to live without this abstraction. So some of the things we have created can still help you measure uncertainty and all, but will not have that capability. Any students have any questions? Everyone is strangely silent, so.
Absorbing.
Absorbing